Okay, so is it better to be biased or unbiased? So biased, again, remember, it's not the English definition of bias. It's not like when people are talking and they use the word bias, it's the math definition of bias. So the math definition of bias is, let's write it down. The math definition of bias for an estimator, so something that estimates, you're asking, you have some value, theta hat, so you estimate some value. There's some real value theta out in the universe, and you estimate it with theta hat. When you estimate, of course, you're not going to get the perfect answer. Sometimes you'll have an overestimate, sometimes you'll have an underestimate. And unbiased means that on average, it is equal to the true thing. So this is unbiased means on average, they are equal. On average, they are equal. Okay, it's a very nice, desirable property. You might think sometimes I'm over, sometimes I'm under, but at least on average, I got it exactly right. Yeah, there's a famous joke about statisticians where the three statisticians go hunting, and they are shooting at the duck, and one of them shoots to the left of the duck, and one of them shoots to the right of the duck, and then the third statistician yells out, "We got him!" That's the joke. It's not a great joke, but on average, did you get the duck? Okay, that's what unbiased means. So what did you guys say? Should we be unbiased? Let's see what you said. Okay. Only 3 people said it's better to be unbiased. I think this is the most tempting thing, that you should always be unbiased. And that one is wrong, so good. Only 3 people picked that one. 6 people picked it is better to be biased, and 7 people picked it depends. I think that sometimes you do want to be unbiased. So maybe there's something you're measuring in real life, and it's really important to you that on average you're right. You know, so like maybe you're measuring something a bunch of times over and over again, and you're going to make some like choices based on the values you get. So for example, if you want to estimate a population and you want to make sure that it's fair, this population versus that population, and the thing you are estimating is something you care about, then sometimes you do care about being unbiased. So it's not that you should never ever be unbiased. Sometimes this really does matter. So sometimes this is good, sometimes good. But the majority of you, I think, figured out what is going on in the video and the topic we're starting, which is that it's not always good to be unbiased. So the answer is it depends. If you really care about being unbiased, then sometimes you want to be unbiased. But sometimes it's better to be biased. And the reason is being biased can actually lower the mean squared error, or whatever error you're doing. So this is, I think, the surprising thing, the surprising fact about reality is unbiased estimators are not optimal for minimizing error. Unbiased estimators, let's say, may have higher error. May have higher error. So if the thing you actually care about is lowering the error, then it is sometimes better to use a biased one. Let's write this one both ways. Unbiased estimators may have higher error, or another way to say it, biased estimators may have lower error. Estimators may have lower error. So sometimes you really care about the value you get, and you really want to estimate theta, and it's important to you to be unbiased. That happens a lot in classical statistics and things like that. Sometimes you're just working at Netflix and you want to just get it as accurate as you can. You just care about how big is your error. And then you don't really care about if you're unbiased or biased. You pick whichever one has a lower error, and sometimes the biased ones have lower error. So in some situations, we want to do this. And this is what we're going to be looking at for the next couple classes. And in particular, something called shrinkage methods. Also sometimes called regularization. And that's what we're going to look at. And these can improve your error, they can lower your error, and we're going to see how it is related to other things we've done in the course. So this is like taking everything we've done and it's putting like a little extra fancy sprinkle on it of adding on this new move you can do to make things biased to try to lower your error. And the very first example is the one from the video on just estimating a very simple Gaussian. So let me try to make this a good size and show you what this is. So here's the problem. you are given n data points, which are all like independent dice rolls. Okay, but they're not actually dice rolls. They're independent Gaussian random variables, and they have some mean, mu sub secret. Of course, in the code, mu sub secret is some number. In real life, you only see the samples, and your goal is to estimate mu sub secret. Okay? And so here it is. I have 4-dimensional data, and then I have 10 to the 4, that's 10,000 samples. Okay, I'm mixing up the numbers. So, n data is 4. That means you're given 4 samples. And I'm going to repeat the experiment 10,000 times. So let's write these down. So, so here is the example problem to try to get this in our brains. And as always, I start with the world's simplest example problem that shows us what we're looking at, and then we build up to real data sets. So n data is the number of data points we have. This is 4. And we are given n data samples, must estimate mu secret. Of course, mu secret we don't know. Our data samples are mean 0, not mean 0, they're mean mu secret and variance 1. And by 1 I mean identity. It's a vector. And these are from some dimension. In this case, I think it's 10-dimensional. Mu secret is in R to the n dimensions. What did I call it over here? N vars, number of variables. Let's go with vars. That's a nice one. Because dimension can mean lots of things. Okay. Okay, so in this case, n vars is 10. N vars is 10. So you're given 4 samples, each of which are vectors of size 10, and they have mean mu secret. That's what you want to know. And they have variance 1. So they have variance 1, and they're independent. So here is the mu secret. Okay, in real life, you don't get to see what mu secret is, but in my notebook, you do get to see. It is 3, 0, negative 4, 0, 0, 0, 0, 0, 0, 0. So a lot of the components are 0, but there are 2 components that are 3 and negative 4. In real life, you only get 1 data set, but because we want to see what happens on average and things like that, I am repeating the experiment 10,000 times. So in real life, you get 1, but for us, we're going to do it over and over again. Here is what it looks like. And the most obvious thing, or the simplest thing you can do, is the unbiased estimation. So unbiased estimation. How do you estimate the value of mu secret? You just take what you have and you average them up. So here is the unbiased estimation. Which is the world's simplest thing. Mu hat equals 1/4 times x1 plus x2 plus x3 plus x4. So you take your 4 vectors that you're given, each of which live in R to the 10, they're 10-dimensional vectors, and you average them up. And this is, okay, of course, this is a random quantity, so you're not going to get mu secret exactly. It's a hat, but on average, you do get mu secret. So the expected value of mu hat equals, and you can look at the formula, you do the expected value of this sum, x1 plus dot 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 plus x4, and that is equal, each of these on average is equal to mu hat. So because expected values are linear, we can bring that in, and each of these is equal to the secret, mu secret. So on average, each vector, even though it's some random direction, on average, it points in the direction mu secret. So if you do average them all together, then that's averaging them all together. 4 copies of mu secret divided by 4, that is also mu secret. So we've just proven that this estimator is unbiased. It's unbiased. On average, this estimator gives you the right answer. And in real life, maybe you want to be unbiased. Like maybe that's important to you. Maybe it's some like political process and you need to be fair. And so like the unbiased is important. You don't want to overestimate or underestimate anything. That's what it is. I'll show you what this looks like in the code, which is, I drew some little histograms. So I averaged it the error, the average mean squared error, was 0.25. And here's what the estimates look like. Remember, I repeated the experiment 10,000 times. So I have these histograms with 10,000 counts in them. And here is variable 0. Variable 0, the true answer is 3. That's the dotted line. And sometimes I'm a little over 3. Sometimes I'm a little under 3. But on average, you can see I'm equal to 3. Very nice and unbiased picture. Variable 1, the true answer is 0. That's the dotted line. Sometimes I'm a little over. Sometimes I'm a little under. But on average, I got it just right. Got the duck. Okay. So that is unbiased estimation. I want to just ask one hypothetical question here. So this is what everybody does. Here is another unbiased estimator. Another unbiased estimator. Okay. Here's the unbiased estimator. Everybody knows 3 is a lucky number. So instead of doing a quarter, a quarter, a quarter, a quarter for the 4 samples, you put more weight on the third one. So mu hat equals, let's do half of mu 3, of x3 rather. x3. And let's do, with our remaining half, I guess I do a sixth x4, a sixth x1, plus a sixth x2. Okay, so I have my data points 1, 2, 3, 4, and because 3 is a lucky number, I put more weight on x3. Okay, so before I was doing a quarter, a quarter, a quarter, a quarter. Now I'm doing a sixth, a sixth, a half, a sixth, and I claim it's still unbiased, right? So the expected value of mu hat, what is it? Well, it's 1/6 times mu secret, because x1 is a mu secret on average. x2 is also a mu secret on average. x3 is also a mu secret on average. And x4 is also a mu secret. So on average, this estimator that I came up with is 1/6 mu secret plus 1/6 mu secret plus 1/2 mu secret plus 1/6 mu secret. So on average, it is mu secret. So there you go, unbiased estimator. So in fact, you can make lots of unbiased estimators. You don't have to do a quarter, a quarter, a quarter. That is totally optional. This one, in terms of being unbiased, is just as good. Okay. Now there's a question. Which one is better and why? Let's have a little vote here. Let's say option A, the first one is better. Option A, first one is better. Option B, second one is better. But more importantly, why is one better than the other one? And how would you tell which one is better? Like, can you prove that one of them is better than the other? I'll let you guys think for a minute. I'll make a question on mathematize, and I'll open this up. I think this is a great question to see if you understand what's going on. Which estimator is better? The first one, a quarter, a quarter, a quarter, or the second one with x3 is lucky? Don't forget x3 is lucky. That's important. Okay, go think for a few minutes while I make the question. Okay, so I opened up a word cloud for the question which one is better and why. So you should put in A or B at the beginning. So there's option A and option B. So start your answer with the letter A or the letter B, and then explain, why. Like, tell me because blah blah blah. Option B is better because 3 is lucky. Yeah, that's a great answer. Okay. So tell me what you think in the word cloud. Or maybe, sometimes A is better, sometimes C is better. Maybe that's true. I don't know. Then you say, could be either. Okay, 10 seconds left. The last 10 people need to put in their answers. Maybe you don't know why, so you say option B, I don't know why. That's a good answer as well. Okay, let's see what people said. Reveal counts. And we get the word cloud. Okay, so I'm seeing a big B and a big A, and they're approximately the same size. Maybe B is even a bit bigger. So maybe more people said B. That's very interesting. Let's I want to see the submissions. Okay, B, I don't know, B. Yeah, put more weights on the better estimator. B, it depends on the problem. B, A, because B is by chance. Well, I don't know, B doesn't have any randomness in it, right? I chose the numbers 1, 6, 1, 6, 1/2, 1, 6. It's very much just like you have 4 numbers, and you need your 4 numbers to sum up to 1 to be unbiased. In one of them, they picked a quarter, a quarter, a quarter, a quarter, and the other one, they picked a sixth, a sixth, a half, a sixth. So, okay. B, A. This is a very reasonable sounding one. There's no reason that X3 is better. When I said that 3 is lucky, I was lying to you. 3 is not lucky. All the numbers are equal. There's nothing special about X3. It's not actually lucky. If somebody tells you it's lucky, they're lying to you. So this one, there's something suspicious, which is you treated the third variable different than the other ones, and that somehow violates the symmetry of the problem. Like x1 and x3 are supposed to be interchangeable. If you had gotten the data set in a different order, you get a different value. So that's suspicious. On its own, that's not wrong, but it's suspicious. Okay. A or B. Okay, this is a very logical thing to say. Both estimators are equally good because they are both unbiased. That's a very reasonable thing to think. Unfortunately, it's wrong. So one of them is better. So two things can both be unbiased. Unbiased is a nice property, but unbiased on its own does not tell you how good it is. All right. So this is a thing. Could be either more weight on the important variables is better. So you might think. So you might think putting more weight on 3 is better. Maybe that's better. But again, x3 is not special. Like, why did I do x3 and not x1? Okay. A, I don't know. B takes into account the weights of the coefficients. Either A or B. Okay, maybe the same idea as before. A, because the weights are equally distributed. So A kind of has this nice symmetry. Why should the weights being equally distributed actually help? There's a very specific way to measure. Okay, yeah, you guys really fell for my x3 is lucky. All right. The luckiest is given the highest weight. Okay. This person was first. Congratulations. Okay. So there is one specific way we need to measure how good an estimator is. Okay? And we got to calculate it for these two estimators and see which one is better. That's what we need to do next. So someone says, I'm doing it this way, and somebody else says, I'm doing it that way, and you should be able to calculate, okay, if you do it this way, you get this, and if you do it that way, you get that. So what am I talking about? What is the way we measure how good things are in this course? And what do you get when you try it on these two things? So let me open up a word cloud for what is the thing that we're going to do. And if you know the thing we're going to do, you can try to do it. But I will give you a minute to think, to try to remember, how do we measure how good things are? So it's not true that unbiased is the same always. We have a measure of which one is better or worse. That's what we got to use to figure it out. Let me open up a word cloud and see if you guys can remember this fact. I guess this is from a few weeks ago now, so maybe that's why you forgot. But I'll give you 1 minute for a new word cloud of how do we measure which estimator is better? What is the measurement device that we use? Okay. And I will open this one up for just 1 minute. And if you know what it is, try to calculate. Try to calculate. Okay, like 10 seconds left. How do we measure which one is better? Okay, put in your final guess. Which one is better? And how do we measure it? Okay, and this time people said mean error, mean squared error, MSE. Somebody wrote variance. It's going to turn out that in this case, the mean squared error is exactly related to the variance. So this person is wrong in general, but is correct for this problem. You'll see that in a second. Maybe they knew that, maybe not, I don't know. A mean squared error. So again, this one, in this particular case, you're gonna see that this is accurate. In general, it's the mean squared error. You can take the square root and make it the root mean squared error. That's more interpretable, but whichever one has the higher mean squared error will also have the higher root mean squared error, so that's the same thing. So looks like most people got it. Root mean squared error. Maximum likelihood, remember the mean squared error is the likelihood of something. So if you did maximum likelihood with the right thing, you will also get the mean squared error. So they're related. Okay, so lots of people did it. This one is not right because this is for classification and we're doing regression. We're estimating a value. This one is like how often you got it right in a classification problem. Okay. Cross-validation, remember, is trying to estimate the mean squared error, the true mean squared error, by using a test set. So when you do cross-validation and get a test error, you are attempting to do the root mean squared error. All right. Did everyone say that? Okay. Very good. So let's do it. Let's do it in this case. And you could do it all from scratch. So you really could compute the mean squared error is the expected value of what you got, mu hat minus mu, all squared. That's the mean squared error. Of course, mu hat and mu in this problem, I guess mu, I've been calling it mu secret. I should call it mu secret. That's what you would do. That's what we did in the first few weeks of class. There is one thing that is a little bit harder, is that these are vectors. They are not numbers. So you can't square a vector, but you can ask for its length squared. And this is the mean squared error in this situation. You take the norm, the length of the vector, and then you square it. This is also equivalent to, by the way, you could also do the sum from I equals 1 to num vars and just do all the components squared. So you do mu I minus mu secret I, the components squared. Okay, so that's what it is. You could start from scratch and you could work through it and figure it out. Fortunately for us, we've already done some work with this and we already know something very nice that helps you understand what's going on here, which is the bias variance trade-off. The bias variance trade-off. And it's not hard to prove. We did it earlier in the course. So the bias variance decomposition, it tells us, actually to calculate this thing, you can look at the expected value of mu hat. So you can, instead of doing some complicated thing with mu hat and mu inside the expected value, you can look at the expected value of mu hat minus mu secret. That whole thing squared, this is what people call the bias squared. Bias squared. Right, okay, bias, that's squared. The bias squared plus the variance. And the variance in this case really is the variance of mu hat. Okay, I guess in this situation it's the variance of the norm. Let's write it like this. The sum of the components, I equals 1 to n bars mu hat I. So how much are the things varying? Once again, these are vectors. You can't do a vector squared, but you can do the norm squared. So how big? How big is this difference? It's a vector. How big is that vector squared? Okay. In our problem, both things are unbiased. So in our problem, both things are unbiased. So the bias equals 0. The first term equals 0 in our situation. But the variances are going to be different. How are we going to calculate the variances? Let's do the variances. Let's do option A first. And I'm going to show you how to do the variance. The nice thing about variance is the variance of independent things adds. So when you do a quarter plus a quarter plus a quarter plus a quarter, you're doing the variances add. So what it is going to be is 0 plus, and it's going to be the variance of a quarter times x1 plus the variance of a quarter times x2 plus the variance of a quarter times x3 plus the variance of a quarter times x4. That's going to be in option A. In option B, same kind of situation. So 0 from the bias, but now the variances are not a quarter, a quarter, a quarter. They're a sixth, a third, and a sixth. Not a third, a half. Okay, good. Okay, so that's what makes these two things different. They have different formulas, and so the variance is going to come out differently. And the one thing you should know about variance is square E. Variance is like the size of something squared. And so when you multiply by a quarter, when you pull it outside of the variance, it's going to come out with a quarter squared. So in option A, we're going to get 0 from the bias, and then we're going to get a quarter squared, and then we're going to get another quarter squared. Let me write it like this. A quarter squared is coming out plus a quarter squared plus a quarter squared plus a quarter squared. And the actual, it's all going to be multiplied by some constant, which is the variance of just any x on its own. That's some constant that gets pulled out. The important thing to focus on is where do these quarters come from? And to use the fact that variance is a quadratic form, so variance is square E. Let me write that fact down. So the variance of c times x equals c squared times the variance of x. Variance goes by the square. So a quarter squared, a quarter squared, a quarter squared, a quarter squared. Whereas the other one is going to be a 6 squared plus a 6 squared plus a half squared plus a 6 squared. All times the same constant. And now the question is, which one is bigger? Which one is bigger? A quarter, a 16th plus a 16th plus a 16th plus a 16th. We have 4 copies of a quarter squared. That's a quarter. So this one is a quarter times the constant, the variance of the individual guy. What is this one? Well, just this term, 1 over 2 squared, on its own is a quarter. And then you're going to add on a little bit more. So this is a quarter, and then you're going to have 3 copies of 1 over 6 squared. I guess that's a 12th. Okay, so which one is better? That one's better. It has a lower error, right? This has higher error. Look, I just proved to you why it has higher error. It has higher error because it has higher variance. And the reason it has higher variance is because this combination of numbers, when you square them, is higher than the numbers before. So even though they're both unbiased, one of them has lower variance than the other. This is why you want to sort of spread the numbers out as much as possible and make them all equal to a quarter. By spreading them out as much as possible, you have lower variance. You're relying on each number individually less. In this estimator, because you have a 1/2 in front of the x3, if x3 comes out wrong, like it's not pointing, it's far from its average, you're going to pick up a lot of variance from that term, and that's what makes it worse on average. So now we've compared these two options, option A and option B, quite thoroughly. And the right answer is, of course, option A is the best one because it has lower variance. And in fact, I believe it's possible to show that option A is the best unbiased one you can do. So from what we've shown over here, first of all, you got to show that doing, you got x1, x2, x3, x4. Could you put any numbers in front of them and come up with a better unbiased estimator? That would be a nice problem to do. And you could prove that option A is the best possible one. Okay, so that's it for unbiased estimators. And so now the surprising thing is that there are bias estimators that do even better. And one example is the one from the video, which is the James Stein estimator. And I think the most surprising thing about this is people did not discover this until like halfway through the 1900s. Like it's pretty new, and people just like didn't know that you could do this. It's like really, really crazy. And what this does is it provides a shrinkage parameter. So there's this called lambda JS, lambda James Stein, which has some formula. I'll get the formula in a second. But then the new estimator is not a quarter. The new estimator, let's call it mu hat James Stein. It's the old estimator, mu hat, that we had before. So that quarter multiplied by this shrinkage factor, lambda s. And the shrinkage factor is in the range 0 to 1, so that's why it makes it a shrinkage factor. It shrinks the original estimate. Shrinkage factor. So we're shrinking the value. There's some formula for it. I don't want you to worry about what the formula is right now. I'll put up the formula in a second. The point is that when you do this, the mean of mu hat JS, because you multiply by this lambda, is going to be less than mu hat mu secret. So because you multiplied the unbiased thing, this one was the unbiased. Let's call this unbiased. That's the one from before. Because you multiplied it by some number that's between 0 and 1, you shrunk it down. And when you shrunk it down, it's no longer on average correct. It's sort of on average less. There is one major problem with what I wrote on the board. It's like morally true, and it's like what I want to say. But it's not technically correct. Does anyone know what the problem is with what's written on the board? If you write this on the board in math class, then the math police come and arrest you. So we're in data science class, so I wrote it. But if you write it in math class, you'll get arrested. What's the problem? Let me give you guys a minute to think. Try to come up. What is the issue? There's something that's like blatantly wrong on the board where you're like, you cannot do that. Like it's not that it's like you did something and it turned out to be incorrect. It's like you wrote something down that you're not even allowed to do. You know, it's like taking the square root of a negative number or something, right? It's not that it's incorrect. It's just like you're not even allowed to do that. All right, I'll let you think for a second. Okay, who wants to tell me, or does anyone have any guesses? What is the thing that is the math police will arrest you for? Yeah.
Is it one view is not one-dimensional?
Yeah, it's not one-dimensional. That's right, exactly. So less than is something you do with numbers. These are not numbers. So if you put a less than sign between two things that are not numbers, then that's not even allowed. So if I have two vectors, if I have the vector, I got the vector 3, 1, 7, and the vector 2, 8, 4, and I say this vector is less than that vector. It's like you can't do that. Vectors are not things that are less than other vectors. And these things are vectors here. So it's a very nice idea, and it's like what we're thinking of. You took the vector and you shrunk it down, and before it was unbiased, and now you shrunk it, so it should be like less than in some sense. What we mean is it's closer to 0. So you could replace this with closer to 0, or you could look at the components. Okay, I think that's the easiest way to fix it. So this is wrong because they're vectors. Not allowed for vectors. But you could look at the components, and then you could say the expected value of mu hat JS, the ith component, is less than the ith component of the secret. Right? So you took the value and you shrunk it down, so now it's smaller. So this one is allowed. The math police will not put you in jail because this is like a valid statement you can make now. Unfortunately, this one is wrong. So before it was not even allowed, and the math police were like, what the hell are you doing? You can't say less than between two vectors. Now it's not true. There's a reason it's not true. Does anyone know the reason it's not true? Yeah. When it's negative, exactly. So when you shrink something, it gets closer to 0. Does less than mean getting closer to 0? No. Less than means to the left on the number line. So what I should say is the absolute value of this is less than the absolute value of that. It got shrunk, right? So I think the easiest way to remember is it got shrunk. It's closer to 0. And we'll see that. I'll show you what it looks like in the code. So here is the variable. This was our unbiased estimator. Remember, the mean was 3, 3, 0, and -4. When you do the estimator, you calculate this shrinkage parameter. There's the formula that I didn't want to write. The formula is some formula. The amazing thing is that these guys proved something about this formula. For us, the only thing we need to know about it is that it's some shrinkage factor between 0 and 1, and that people proved that it has a better error. So they multiply by this lambda, and then they shrunk things down. So here's what it looks like now. Let's see if I can get this whole thing. So before, the mean was 3. Now we repeat our experiment 10,000 times, and you see that our estimates for the first component in variable 0 are a little bit to the left, right? They're smaller than 3. We're estimating things that are like 2.5 on average, and we shrunk it a bit. For variable 1, the mean was 0, and we shrunk it a bit, so the mean is still 0, right? The mean was 0 before, now the mean is still 0, because you shrink 0, it's still 0. So I guess this one is still not right, because it should be less than or equal to. Less than or equal to. Okay, there we go. But this is where the negative can go wrong, right? So if you shrink something whose mean is -4, it gets pushed to the other side, it gets closer to 0, and shrinking in this case means getting bigger. So it can get bigger or smaller depending on if it's negative or positive. That is the James-Stein estimator. And if you're looking at these graphs and you're like, which graphs are better? This is the James-Stein estimator, these 3 graphs, trying to estimate those dotted lines, or are they the ones we did before, these ones? And you're like, look at them, and you're like, well, that looks better, right? Like on average, it's correct. But then you go to compute the mean squared error, and the mean squared error is smaller. It's 0.234, and before it was, what was it? 249. So it shrunk by like 10%. So this James-Stein estimator in this case is like 10% more accurate in terms of having a 10% lower mean squared error. That's the thing that is very surprising. So it has a lower, and this is the thing they proven that the mean squared error for just mu hat unbiased is worse than the mean squared error of the mu hat James-Stein. Okay. And if you haven't ever taken a course on this stuff and you don't know what's going on, this is extremely surprising because you might think, oh, the bias is just like the size of the error. Like the more bias you have, the more error you have. But that's not true, and we know that. We know that the mean squared error has 2 parts. It has a bias and a variance. And this is why things work. So the mean squared error of the unbiased estimator, that was 0 squared plus some variance. The mean squared error of the James-Stein estimator, the mu hat JS, so now it is biased. So the bias term, before it was 0, now the bias goes up a bit. And in fact, the bias, I can tell you exactly what it is because I know exactly how the mean changed. You multiplied by this lambda parameter, and so very roughly speaking, you kind of did the mean was, it's something like this, lambda JS times mu hat minus mu hat secret, right? All squared. So it's like how much you shrink minus the original thing squared. That's approximately like 1 minus lambda JS squared, maybe up to some constants. So because it's a little bit smaller than 1, this bias is a little bit positive. So you're introducing a little bit of bias with a square. So you might think, oh, that's worse, right? You made it worse, right? Before we had 0, that was the best possible number. Now we made it worse. Why on earth would we do this, and why is it better? Well, the reason is this term gets worse, but the variance term, that gets better. Okay, so the variance is the thing that is improving. That's the reason the James-Stein estimator is doing better. We have shrunk the whole thing, which introduces some bias, but it also shrinks the variance. And because variance shrinks like the square, right? Remember, variance is shrinking like the square. When you multiply by something, you shrink by the square. So the variance, it shrunk by, again, also something involving lambda js squared. Okay? So the amount you increase the mean and the amount you decrease the variance are both kind of proportional to this lambda js squared. And so by getting it just right, you can actually decrease the overall mean squared error. And that is what those James and Stein guys proved, is that on average, it's getting a little bit better when you do this James-Stein estimator. And that's what we showed. So look, we did it, and the variance decreases, and that's what makes the whole thing work. And so you have a slightly lower mean squared error. Okay, hooray for us. This is a great place to stop if there's any questions or comments on why these things work. Because we're going to look at other versions of this. I think this is the simplest one where you can conceptually understand what's going on and why it works. And we're going to do more complicated ones from here. This is a great place to stop for questions. Okay, question for you then. What happens, instead of using this fancy formula, what if I just make up a number and I just say, like, let's do 0.9 times mu hat, right? So instead of these James-Stein guys who are smarter than me, who came up with this fancy formula, let's try the new way, the simple way. Let's just try mu hat. The new one is 0.9 times the mu hat, the unbiased one. Is this going to work? That's my question. And you tell me, what do you think? Is this going to work? Yes or no? And I have mathematized for you. So this is the constant shrinkage factor. So in the James-Stein estimator, it depends on how things came out. And they did it in a very clever way. But now I just want to try a constant. So let's just pick 0.9, and we'll just shrink by 0.9. That'll make the math even easier. Could this work? I wrote select all that apply. But of course, it's either yes, it can still work, or no, it won't work. There's only one option. So select one. I'll let you think for a minute. Based on what you understood from before, do you think this is going to work or not? Maybe I will bring up the justification again. Could this work? Okay, put in your final guesses. Do you think it's going to work, or do you think it's not going to work? And what did people say? Is it going to work or not? 11 people said, yes, it can still work. 5 people said, no, that won't work. And of course, the answer is yes, it could still work. Here's the thing, though, right? The James-Stein people, they did this fancy proof that it definitely works. So they had a fancy formula, and they had a fancy proof that it's definitely going to work. If you do it with a constant, then everything I said still applies. So you are shrinking so mean squared simple. Let's add a line for mean squared simple. Mean squared error of mu hat simple, where the simple one means you multiply by some lambda. Everything still works. So you are increasing your term by like 1 minus lambda squared, and you're decreasing the variance by like lambda squared. And it's potentially possible, depending on how big these constants are, that you've shrunk it overall. It's also possible you made it way worse. So you got to be careful, right? You're shrinking the variance term, and you're increasing the bias term. If you do it the wrong way, you're going to get a worse error. And if you do it the right way, you're going to get a lower error. How could you check and see? I believe that is the next mathematized question. Real life. Okay, yeah, before we do this one, let me show you what this looks like in the code. So here it is. I'm just trying a fixed shrink factor, right? So just for any lambda, we can try this out and see if it works. And so I have a function called try shrink factor, and it just tries a bunch of them. So I'm trying all the values of lambda between 0 and 1, okay? And we're looking at the mean squared error, and we want the lowest possible mean squared error. You see when lambda equals 1.0, that's right here, at the very tippy tip over here, that's doing nothing. If you shrink by a lot, like if you put in lambda equals 0.2, you have made it much, much worse, right? So if you try a shrink factor that is like 0.5 or something, you make the error way worse. But if you do 0.9, it's a little bit better. And I have a little zoom in here to show you how it works. So here is 0.8 to 1.0. And you can see that 1.0, that's the regular thing, no shrink factor. Then you have an error of 0.25. And you can make it better as long as you try a shrink factor at like 0.9, 0.92. You made it a little bit better. If you make it too small, it gets worse again. So you gotta balance the variance and the mean. You're making the bias worse, but you're making the variance better. And that is perfectly optimized right here at 0.9 for this problem. All right. Here's the thing though, I did kind of cheat and I calculated the real mean squared error, right? So when I calculated the mean squared error, I used, in my function, I used mu secret. So what is the mean squared error? It's mu shrink minus mu secret. So I took the secret value and I computed it. In real life, you don't know the secret value. So what should you do? And that's what I have over here. We can estimate the mean squared error for different values of shrinkage by using what? So you can't make the graph that I just made because I cheated and I used the secret, but you can do something else. And I'll let you remember from earlier in the course, how can we do it? Let me give you 1 minute. Okay, 10 seconds left. Try to remember, how can you get around this cheating of looking at the mu secret? Okay, let's see what you thought. What did people say? In big letters, cross-validation. So if you wrote cross-validation, that's exactly what you should do. CV, cross-validation, all of these are great. Bootstrapping. I wonder if bootstrapping could work. Oh, I suppose you could also do it with bootstrapping and then like pretend that, yeah, then you do like out of bag error or something. So yeah, test train split, that's exactly it. So this is what the trick we've been doing all the time. You can check and see if your shrinkage method worked by just using cross-validation. So this is like the simplest form of everything we're doing for the next week or so, right? Shrinkage methods. Instead of trying to be fancy, just try it and see if it works. Shrinkage methods. So what is the big idea in two methods, in 2 words? Step 1 is shrink your estimates. Your estimates. And the reason this might work, or potentially might work, is because this lowers variance. Lowers variance. It increases bias. Or more accurately, increases the bias squared. So by shrinking things, you lower your variance. You do increase your bias squared. And so you should check using some method, for example, cross-validation, to see if things are actually improving. cross-validation to see if it actually helps. Right? So because you're lowering it in one way and increasing it in another way, you got to make sure that you're actually helping things on average. So this is what we're doing. And also, because this is lowering the variance, you could also make an argument, and people do all the time, that we are making sure we don't overfit. This helps overfitting. Right? So overfitting happens when we are sticking to the training set too much, and overfitting, another way to say it, is the variance was too high. So because these shrinkage methods, they lower the variance, they also help with overfitting. That's like an equivalent thing. Lowering the variance and overfitting are sort of equivalent ideas. Okay, so I've shown you the very basics. I've shown you the James Stein one, which is the simplest possible thing. And we're going to start learning some more complicated ones now. Okay, was there anything else in here? Okay, these are what these look like. So if you do a shrinkage factor of 0.9, you get like the optimal thing. In real life, you would just try a whole bunch, and then you would use cross-validation or bootstrapping or something to tune this parameter. How much should you shrink it? So that's our very first example. Any questions or comments about this one? Okay, let's learn. Nobody uses this one in real life because it's very easy to make one that's better, and I'm going to tell you about that one now. That one is called ridge regression. So ridge regression. So I guess example one was just shrink everything by some fixed parameter. Just shrink all values by lambda. That's what we just did. It technically works, but you can improve on it quite a bit. And so example two is going to be in the context of a linear regression. So again, you could just shrink everything by lambda. Like you could take example one and just do it. That would work. But you can do something even smarter, which is we shrink using a penalty. Okay. And you'll remember when we do linear regression, we are finding the over all possible parameters in our training set. So we're looking at the minimum over all possible parameters theta of our estimate, which is f of theta x minus y squared. And this is summed over our training set and train xi, yi. So this is what we did before. We were minimizing the square error, and we talked a little bit about how to do this with derivatives. There's other ways to do it. That's what we did before. So far, it's just regular linear regression, but we're going to add on a penalty term, And the penalty term says, don't just minimize this. Minimize this plus something involving theta I squared. So it's sum over parameters. Let me use a different letter. Let's do j for parameter. J. J equals 1 to number of params. So basically, if you make the parameters really big, you're going to pay a big price in this penalty. If you can shrink the parameters, like for example, if you made all the parameters 0, then this would shrink down to 0, and you would pay no penalty, right? So this you should think of this as a penalty term. We're trying to make the computer shrink the parameters. Instead of just doing it and saying, look, you have to shrink all the parameters by 90%, we're letting the computer pick how much it wants to shrink by imposing a penalty term. So it's a little bit like you take a rolled up newspaper and you hit the computer and you say, bad computer, make the parameters smaller, okay? And you like, this term is telling you how to do it. In this one, we just did it for the computer. In this one, we're telling the computer, look, you could make them big. Like if you want to make the parameters big, that's up to you, but I'm holding this newspaper, so don't, okay? That's what we're telling. And to tune things, before we had this parameter lambda, and we could check and see how much we want to shrink. Of course, if you shrink too much, it's bad. So we need to be able to tune the shrinking amount. Here, we're going to introduce something called beta. Some people call it alpha. I think let's call it alpha. I think that's what I called it in my thing. Alpha. And alpha is how much to how strong of a penalty. Alpha equals how strong the penalty is. So alpha equals 0, no penalty. If you put alpha is the biggest possible number, That's like saying, look, you're going to get a huge penalty for this term. So if alpha is really big, then all parameters will be 0. So that's the other side of the spectrum. If alpha equals infinity, all parameters are 0. So you should compare this to what we did before with the lambda. If you want to compare this to the lambda, if lambda equals 1, then you do nothing. And if lambda equals 0, then all parameters were 0. So it's a little bit like the spectrum of how much you want to shrink lambda from 0 to 1, but now it's going from 0 to infinity. And it's a slightly different interpretation because of this penalty thing. And the smart thing about this penalty is that the computer can shrink different parameters by different amounts, right? So you can do something different to theta 1 than you did to theta 2, whereas in my estimator problem before, it was all getting multiplied by the same lambda. So this is like a much smarter way to do it, and it turns out it has some nice math too. So this alpha also makes this thing easier to solve in some sense, which is very surprising. So this is called ridge regression sometimes, or L2 penalty regression or something called ridge regression. I have no idea what it has to do with a ridge. I don't know who invented ridge regression. Very weird name. Some people call it the L2 penalty, or L2 regularized penalty. L2 regularized. And the reason they call it L2 is because this thing, where you do the sum of the squares, is the L2 norm. Whatever power you put over here, that is the P in the LP norm, and in this case it's the L2 norm. Let me erase this too. Okay, so that's the ridge regression, and that is the simplest possible thing. And again, it works exactly for the same reasons that the James Stein and the shrinking works. When you shrink everything, you increase the bias, but you decrease the variance, and that can be favorable for you. I'm going to show you some examples in a second. Any questions or comments about this idea? Yeah?
You mentioned you could apply different weights to every parameter.
So this is a great question. So far I've only used one parameter lambda for everything, and in this one, there's one parameter alpha that gets used for everything. Are you asking me, could you use more than one parameter?
I just wanted to clarify, but you mentioned earlier that you could have the alpha be a different weights for every parameter.
So you could do that, right? So in the classical ridge regression, you just have one alpha, which is a real number. You're saying, could you do like the sum of j equals 1 to the number of parameters, and then you could have alpha j times theta j squared. You could totally do this. So this is like totally valid and could work. The problem with this is usually the number of parameters is extremely high, and so now you have an extremely high number of alphas that you have to figure out, right? So when I was doing this, I only had one parameter lambda, and I was like, let's try a bunch of different lambdas to find the minimum. If you did this thing with your alphas, you would have hundreds and hundreds of alphas that you would have to sort out, and you would have to find the optimal value for each one. And to test that, you would have to test them all out, and so that would be very difficult. And you don't want to do that. So it could work, and in fact, if you have like a low number of parameters, this is maybe a good idea. But in a real life problem with a high number of parameters, you've introduced too many parameters. So it could work, but potentially bad, potentially an issue. By the way, these parameters, like lambda or alpha, these are called hyperparameters. And if you have a lot of hyperparameters, that makes it hard to figure out how to make your model good. Hyperparameters. I think I've mentioned hyperparameters before. So you don't want too many of them. You want to keep it manageable. And one is great. A handful would be okay, but you definitely don't want one hyperparameter per parameter. That would be too many. Yeah, great question. Anyone else? Okay, so let's see a simple math example of this, and then I'm going to do an example on a data set. Here is the math example. So here is a data set I made. I got x1, x2, x3, x4, x5, and I have two y values, y1 and y2. I'm going to do them separately. So it's really just like two regression problems in one. And I made this problem on purpose so that the correlations would be really high. So x1 is really highly correlated with x2, and x2 is really highly correlated with x3, and so on. So all of these things are very highly correlated with each other. And you might ask, okay, well, which ones should we use then in our regression? Some people are tempted and they say like, oh, delete all the ones that are highly correlated. If you did that in this case, you delete all of them. So you can't do that. You have to be a little bit smarter. And so yeah, pre-selecting based on correlation is not great. Here's what the data looks like if you just use x1 versus y1, x2 versus y1. Hard to see the difference. But I want to compare. I'm going to do ridge regression at the end of this. For now, I want to do forward selection, which a lot of people did on their projects. So if you do forward selection, you can see it looks like this. So I have here forward selection, the number of predictors versus the test RMSE. So on a test set. And for y1, the best number of predictors is 1. So sort of like the best thing is just use one variable, and the rest of the variables are just confusing you. Like they're adding noise, they're not helping you predict. If you add more variables, you're overfitting too much. Y2, on the other hand, is kind of the opposite. Y2 is like this. So in Y2, you should use 4 predictors. If you use all 5, then you're overfitting. But 4 is the right number to use. So Y1 and Y2 are kind of different, even though they have the same x's. And in fact, when I made the formula, the secret formula, because I can show you because I made it. In the secret formula, x1 is y1 is just b times x1, and y2 is b times x1 plus x2 plus x3 plus x4 plus x5. So, like really, they are. It's not a coincidence that there's 1 and 4. It was on purpose. So that's showing you that. Forward variable selection is minimizing the variance by figuring out which variables to use. And you can figure out 4 variables versus 1 variable, even though the data sets look pretty similar. Okay, that's forward variable selection. Let's do the same thing with ridge regression. And with ridge regression, you're not going to have number of predictors on the x-axis. You're going to have this variable. Called alpha. And if alpha equals infinity, then all the parameters will be 0. That's like choosing nothing. And if alpha equals 0, that's like choosing all 5 variables. And you're going to see there's different trade-offs on what to do. And the nice thing that you can do is you can plot how to choose. You can plot value of theta. This is a dot. Value of theta, the parameter, versus alpha. And you can see how it's changing as you change alpha. So once again, as alpha gets bigger and bigger, all the parameters go down to 0. When alpha equals 0, that's straight linear regression, and you kind of have this spectrum in between. Let's see what it looks like. So here's what it looks like. So here is, in Y1, what do the coefficients look like? Y1. So this is the coefficients versus the regularization parameter. Did I call it alpha? I just called it the parameter. So this is alpha. So here alpha starts really small, 10 to the minus 2 is 0.01. Here it's really big, it's 1,000. And you can see if alpha is 1,000, then all the coefficients became 0. So the coefficient in front of x1, x2, x3, x4, and x5 all became 0. But the sort of exciting thing is to see how they are shrinking over time. So this one, x2, remember, x1 actually only depends on, or y1 actually only depends on x1. So this x2 being -3, this is pure noise. So this is just like completely wrong. The true answer is 0. And you can see that as you increase the ridge regularization parameter, this gets closer to 0. So by shrinking it, we are helping a bit. All right, the real one is 1. You can see there's quite a bit of noise here. But by shrinking it, this shows you how they're shrinking and how it works. You can also plot the size of the errors and the size of the coefficients. So this is, again, on the x-axis, the ridge regularization parameter, and how big is the train set and the test set error. And you can see that it kind of looks flat here, but it is a little bit of a U, and this dotted line is the minimum. So that's for x1. You can improve your root mean squared error a little bit by doing this thing. For y2, it looks a little bit different. So here's what it looks like for y2. And in y2, you can see all of them are sort of shrinking, right? So before, we had one of them shrinking dramatically, and the other one's not moving too much. In this case, they're all sort of shrinking sort of equally. And that's because y2 depends on a lot of these parameters. And you can see more of a U shape over here. So the test set root mean squared error really does have a minimum. You can shrink from like 5 to an error of like 4. So you get a 20% improvement in the errors. So this is all like a very mathematical made up example. But I think it shows you the idea of how you plot these things and how you find the best values using cross-validation. Okay, we're going to do, in a second, I'm going to do one with a real data set. But any questions or comments about the fake math data set? Okay, let's do a real data set. This is a data set you guys have seen before. It is my favorite baseball data set, the hitters data set, right? So we have all these baseball players, and we need to predict their salary. Remember, their salary seems like they're very poor, $480, but they're actually very rich. It's $480,000. Okay, and we have all this information. How many at-bats, how many home runs, blah, blah, blah. Which league are they in? That's new league. Are they in the new league? Which division are they in? There's like multiple divisions. Those are 0 or 1, and you have all these numbers. Like how many 100 home runs they got, whatever. How many times did they go to bat? Things like that. Okay, so here's the ordinary least squares, and here is the ridge regression, and here is the same kind of plot as before. So just like before, I'm doing the parameter on the x-axis, the regularization parameter. It starts at 10 to the minus 2, doing almost nothing. So that's like ridge regression. Sorry, that's ordinary least squares regression. And 10 to the 3, they all get shrunk down to 0. And in between is what we want. You might notice that not a lot of them change. It's not changing much. And that's because I did something dumb. There's a mistake in the notebook. And I want you to think about what the mistake could be. And I'll put this up as the last mathematized question of the day. Issue with ridge on the hitters data set. The improvement is extremely tiny on the hitters data set. Are we doing something wrong? Yeah, so I showed you this picture. Not much is changing. If you look at the value of the error, we've improved from 341.5 to 339.9 or something. It's like a 1% improvement over here. And there really is a bug here. I've made a mistake on purpose that a lot of people make. I want you guys to think about what the mistake could be. And we'll do that as the last thing. So, and we'll take up what the mistake is next class when we do more of this shrinkage stuff. Let me give you a 1 minute to think about it. You can also put in, I have no idea. What